Just picking up with where we have left off, okay, and we were looking at just samples of base 10 and base C logarithms, and with base C logarithms, especially with the natural logarithmic base e, we were crossing over to some business applications to which we will get back. But for right now, looking at what we have for logarithms of all kinds of types and bases, if we look into properties of logarithms, and for properties of logarithms, okay, we have just starting out with single terms, okay, and a common introductory property that we have for properties of logarithms is going to be where you can have a match between the exponential and the logarithmic base. And with the first property, we can say that we have the base A logarithm of a to the x is equal to x. Same parallel to when we first looked into logarithms, when we looked at the interchange of the one-to-one exponential function y is equal to a to the x going out to x is equal to a to the y, and I had eliminated the a in a to the y upon taking base A logarithms in the equation, where we had the base A log of a to the y reduced to y. Well, here, same thing, but with the letter x. We had the base A logarithm of a to the x is equal to x. And just some of the examples that we have for reduction by the use of this property. And we can say we have as first case, all right, say we are looking at, let's say we have just like in your calculator, okay, you have like log of 100. And if you see just log but no explicit base, just remember that log is going to be in reference to a base 10 logarithm. So the base A is going to be 10, and for 100, okay, I can write this in terms of base 10, since 100 is both a multiple and an integer power of 10. So for 100, okay, 100 is going to be 10 squared. So in this framing, okay, so you had the base A log of a to the x is going to be where a is represented by 10 and x is represented by 2. So we have for the base 10 logarithm of 100, okay, that is going to be equal to 2. Okay, also with our other calculator logarithmic base, okay, you have in the appearance of ln, and that is going to be a natural logarithm. And again, have the natural logarithm of e to the negative 4, and natural logarithms are going to be logarithms of base e, and again, e is that 2.718 figure. So the natural log of e to the negative 4, that's going to be the base e logarithm of e to the minus 4. So here we have in this establishment, a is represented by e, x by negative 4. So the natural log of e to the negative 4 becomes negative 4. And also another case, let's say if we have a logarithm that is not in too many typical scientific calculators, say we have a base 5 logarithm, and we'll take that of 125. So for the base 5 logarithm of 125, okay, just as 100 is both a multiple and an integer power of 10, we're going to have 125 to have that kind of relationship with 5, where it is both a multiple and an integer power. And so we have the base 5 logarithm of 125, and for the terminology we have in the exponential base 5, 125 would be 5 raised to the third. Okay, so you have a at 5, x at 3. So we have the base 5 logarithm of 125, okay, becomes the base 5 logarithm of 5 cubed, and that is completely reducible to 3. Okay. Now, for the next property, this is going to be one that's going to be in close relation to the first, and it'll be a while before we had this to resurface after the introduction, but it will loom okay, as we look into ultimately what will be regarded as logarithmic equations. And for this property, we're going to have a to the base a logarithm of x is equal to x. And just examples of what we have for a to the base a logarithm of x. We can say we have 2 to the base 2 logarithm of 5 is equal to 5. Okay, so here a is at 2, x is at 5. And let's say if I have 10 to the log of 2. Again, log will be in reference to a base 10 logarithm. So here in the rewrite, writing explicitly the logarithmic base. So we have 10 raised to the base 10 logarithm of 2, and that is equal to 2. And let's say with the natural logarithmic exponential base e, if I have e to the natural logarithm of 12, and writing explicitly, okay, what we have for ln, okay, so ln is going to be a base c logarithm. So here I'm going to have e to the base c logarithm of 12, where I have spelled out, okay, the a is going to be at e, x is going to be at 12. So e to the ln of 12, okay, a bit reflexive, and that is going to go to 12. All right. Okay, so for these two properties, okay, we're able to write in terms of where both the exponential and the logarithmic bases match up. But now for situations whereupon we don't have quite the match, and we're looking at determining or approximating a value, and we can say we have, for those circumstances, regardless of whether there is a match or not, we're going to have what is often referred to as the change of base formula. And we have here, okay, for the change of base formula, okay, say we have, okay, now when we started out, okay, we had that the base a logarithm of a to the x automatically went to the x, the value of x. A to the base a log of x is equal to x. We were able to apply automatically the simple reduction on the basis that we had a match between the exponential and logarithmic bases. But let's say if we don't have quite a perfect match. And here, okay, say we have a base a logarithm of m. Okay, so just from what we see right away, a and m, not the same letter. And if I were to apply a kind of reduction, one upon where we can use, let's say, a scientific calculator, especially a commonly used one, we can write this as a ratio of terms involving different logarithmic base. Okay, so for the base a logarithm of m, okay, when we say we have a base b logarithm of m, okay, so the base b logarithm of the exponential base or the attachment all over the base b logarithm of the term that was the original logarithmic base. So you had the base b logarithm of m all over the base b logarithm of a, and for your calculator, that base b logarithm, you could either use the natural logarithm, so we can write this ratio as the natural logarithm of m over the natural logarithm of a. Also, if you do not go with ln, you could go with log. We had the base 10 logarithm of m all over the base 10 logarithm of a. And let's say just for cases that we have regarding the change of base formula. Okay, so let's say if we have in this one case. See if we have, let's say just for example, okay, let's say we have so if you were to reduce the following, and we'll say we have to the nearest 3 decimal places. Okay, and we have, let's say that if we have base 2 logarithm, or to what? No, base. We'll go with the base 12 logarithm. So the base 12 logarithm of 176. Okay, and for this one case, so we have for the base 12 logarithm of 176, again, you can either use the natural logarithm ratio or base 10 logarithm ratio. We'll go with ln on this one. So here a is represented by 12, m by 176. Okay, so for what we have in the case of the natural log of 176 all over the natural logarithm of 12, okay, so you have among your first digits, okay, so we have, so you got 2.08075 and some more decimal places. And if I'm looking at rounding to the nearest 3 decimal places, okay, so we have with the 3rd decimal place, okay, so you got 0, and alongside it is the number 7, and since 7 is 5 or greater, okay, that 0 rounds up to 1. Okay, so to the nearest 3 decimal places, we have right at 2.081. And let's say that if we have another case where we have the change of base, and let's say if we have a base 4 logarithm, and we'll say that we have 0.97. Again, you can repeat the use of natural logarithms, but I think we'll go with the base 10 on this one. But if you go with ln, that's fine. Okay, so for m, that is represented by 0.97. And for what we have in the case of a, okay, again, that was 4. Okay, so in looking at taking the ratio, so we have for the base 10 logarithm of 0.97 divided by the base 10 logarithm of 4. Okay, so we got in this one, why did I have 0.4? Okay, so we got 0.97. So we got the base 10 logarithm of 0.97 or the base 10 logarithm of 4. Okay, so we have for the layout on this one, okay, so we have minus 0.02197. Okay, and for what we have for the 3rd decimal place, so that's going to be the 1 here, and with the 9 alongside it, okay, we'll round this decimal place up, and so to the nearest 3 places we have minus 0.022. And let's say that if we have, I started putting a decimal logarithmic base for this previous problem. Let's say if I go at it with this case, and we'll say we have the base 0.7 logarithm of 20. Okay, and again, you can either go with a natural logarithmic ratio or a base 10 log ratio. We'll go back to ln on this one. Okay, so m is represented by 20, whereas a is represented by 0.7. Okay, and so here we have among the first digits, so we have minus 8.39905. Okay, and we have at the third decimal place. Okay, so you have this 9. The 0 alongside it signals that this 9 will remain fixed. Okay, so the nearest 3 decimal places, okay, would come out to negative 8.399. Okay, so for these properties, okay, we have concerning individual logarithmic terms. And now the fourth property, this is going to provide a bit of a segue to interaction between 2 or more logarithmic terms. And again, just providing a little bit of a backdrop. Okay, again, we had the first property at the base a logarithm of a to the x is equal to x. Okay, so we had a match between the exponential and logarithmic bases. But let's say that if you don't have a match, kind of like what we have with the change of base formula examples. But let's say that if we have with an exponent attached to that which represents m, okay, and if I have, let's say, the base a logarithm of m to the r, okay, now because we have a mismatch between the variables, okay, we're not going to have the base a logarithm of m to the r to reduce to that power. Okay, so what you can do with r is that you can go from the power position and write this as a variable coefficient. So the base a logarithm of m to the r, that is going to be equal to r times the base a logarithm of m. And just some of the cases that we have. And again, this is going to bridge a gap that exists for what we have with single logarithmic terms and what we had to play out in terms of operations between logarithmic terms. And let's say that if I have something like the base 3 logarithm of 5 to the t, base 3 logarithm of 5 to the t. So you have a represented by 3, m by 5, r by t. And so we have t in the power position, and I can write this as a coefficient. So in the rewrite, okay, the equivalent of the base 3 logarithm of 5 to the t, we say it's going to be t times the base 3 logarithm of 5. Okay. And let's say that if we have something like the base 2 logarithm, and we have of the quantity of x plus 4 raised to the third. Okay, so this time we have representing m is going to be the binomial x plus 4, r is represented by 3, a by 2, and putting this in the format of r, base a logarithm of m. Okay, so we have 3 shifted out to the front. So we have 3 times the base 2 logarithm of all of x plus 4. So you need to keep the parentheses. All right. And also where parentheses might need to be formed. And let's say that if we have, let's say, a base 5 logarithm, and we'll say that we have t to the y plus 4. So you got the base 5 logarithm of t raised to the y plus 4. Now, again, so you have a at 5, m at t, r at y plus 4. And in the rewrite, I want to signify that whatever represents r is going to multiply the rest of the logarithmic term. So I want all of, in this case, y plus 4 to multiply what's going to be the base 5 logarithm of what remains. So to signify that both y and 4 are multiplying, I need the parentheses. Okay, so we have all of y plus 4 times, okay, the base 5 logarithm of t. Okay, and I'm just going to repeat this a bit. Okay, so we need parentheses for this statement. Okay, and one reason, actually the main reason, is that, you know, when we say y plus 4 times the base 5 logarithm of t, we're looking at all of y plus 4. Because without the parentheses, in other words, you have like y plus 4 base 5 logarithm of t, and without the parentheses, you had the base 5 log of t being multiplied by only 4, whereas y is detached. Okay, so what we mean here, this is not the same of what this otherwise, for what otherwise might be on display. Okay, so again, you do need the grouping symbols. And now, again, I had mentioned that this property kind of provides a bit of a link, okay, to operations between logarithmic terms. Okay, and for what we have for the first set of operations, we're going to be crossing over into the realm of what will be regarded as subs and differences of logarithms. Okay, so for what we have regarding sums and differences of logarithms, okay, so we say we have a base A logarithm of m times n. Okay, so you have inside, okay, you have within the attachment, there are two factors. You have m and n multiplying each other. And now where I have in the single logarithmic term among the factors, wherever I have multiplication, like in the case of m times n, I can form a bit of a detachment between m and n, where I have the capacity of multiplying in the single logarithmic term will spin out to where I'm going to have the multiplication to be written in terms of adding. And for this particular term, okay, we're going to have separating m from n. Okay, the base A logarithm of m times n becomes the base A logarithm of m plus the base A logarithm of n. So multiplication in the single term implies addition once the terms are separated. Okay, now for what I have between m and n, say if I have the base A logarithm of m over n, okay, now in the expansion where multiplication implies addition, in this case we're now going to have division is going to imply subtraction. In this case, the base A logarithm of m over n becomes the base A logarithm of m minus the base A logarithm of n. Okay, so this is what I have in the case of expanding. And I'm just going to mention, if we go in the other direction, this will be where we are looking at combining like logarithmic base terms. So we're going to have the reverse to be true. So I have the base A logarithm of m plus the base A logarithm of m, where we have the addition in the separate terms, but the same base is going to imply multiplication between the attachments once we consolidate as a single logarithmic term. And for what we have for subtraction between logarithmic terms in the same base, okay, that's going to imply division upon consolidating as a single logarithmic term. All right. Now, let's say that with these properties, okay, on the side of expanding, okay, let's say that if we're looking at say some of our various logarithmic terms, and let's say that if we are looking at expressing if we're looking at expressing the sums and differences of logarithms. While writing exponents as coefficients. And again, for that part about writing exponents as coefficients, it's just going back to this fourth property. So any powers I write as numerical or variable coefficients, just depending upon what the exponent is going to be. And let's say that first case here, if I have, let's say the base 3 logarithm of a times b. Okay, so I have the base 3 logarithm, and I have a and b multiplying. So we could say that this is on a parallel or an application of the base a log of m times n. So the base a is represented by 3, m times n is represented by a times b. And upon expanding, okay, so I'm going to detach a from b and write out separate base 3 logarithmic terms. Okay, so with multiplication implying addition, we're going to have the base 3 logarithm of a plus the base 3 logarithm of b as the result. Now, let's say that where we can have exponents to enter the scene and not providing that much of a change up from a times b. Let's say we have a base 3 logarithmic term, and we'll say that we have inside, okay, we'll say that we have u to the second times v to the fourth. Okay, so you still have multiplication going on between u squared and v to the fourth. So converting what we have in the multiplication to terms of adding, so we have the base 3 logarithm of u squared plus the base 3 logarithm of v to the fourth. Okay, and so for what we have writing exponents as coefficients, okay, now before I had a and b are just a first degree, so there was no conversion of exponents to coefficients. But with u and v, u is raised to the second and v is raised to the fourth, and expressing the exponents as coefficients, so the base 3 logarithm of u squared will become 2 times the base 3 logarithm of u, and then followed by plus 4 times the base 3 logarithm of v. Right. Now another special case, and this goes back to the very first property. And let's say if we were looking at the base 6 logarithm of 36 times x to the 6th times y to the 9th. Okay, so you have, so we're sort of expanding the model. Okay, instead of having 2 factors inside, we now have 3. So you got 36 the first, x to the 6th as the second factor in the attachment, and y to the 9th as the third. And again, we have multiplication among the factors. So once I split up, I can write the sum of base 6 logarithmic terms. So I have the base 6 logarithm of 36, and I have plus the base 6 logarithm of x to the 6th, followed by the base 6 logarithm of y to the 9th. Okay, and again, now if you notice, we have 6 and 36, and I can reduce what I have here because 36 is both a multiple and an integer power of 6. Now I'll just duplicate the next 2 terms, and I'll just convert the exponents to coefficients in the last step. All right, so we have for the base 6 logarithm of 6 squared. Okay, so we have a match between the exponential and logarithmic bases. So base 6 logarithm of 6 squared, this will go to 2. And for what I have for x to the 6th, I can write 6 from the power as a coefficient, and for y to the 9th, I can move 9 to the front. So we have in the simplifying, or the expanding rather, so we have 2 plus 6 times the base 6 logarithm of x. Then we have plus 9 times the base 6 logarithm of y. Okay, and that'll be the result in this case. And so far we've had the operation of multiplication in the attachment. And let's say that if I look at, well, we have linking division with subtraction. Okay, so we got this property, base a logarithm of m over n is equal to the base a logarithm of m minus the base a logarithm of n. And let's say that if I have the base 2 logarithm of 4 over b to the 3rd. Okay, so for what I have here, okay, so you have like a is represented by 4, or say m is represented by 4, n by b to the 3rd. So here we have base 2 logarithm of 4 minus the base 2 logarithm of b to the 3rd. Now I'll mention whatever attachment is at the top, then we have a positive logarithmic term spun out. Okay, but for anything that is in the denominator of the attachment, it will have a negative logarithmic term to be formed. Okay, so right now we got for the base 2 logarithm of 4. Okay, so kind of like 36 is to 6. Well, 4 is both, with respect to 2, both a multiple and an integer power. So here we have the base 2 logarithm of 2 squared. And again, we have minus the base 2 logarithm of b to the 3rd. Okay, so we can convert. Okay, so for the base 2 logarithm of 2 to the 2nd, reduction goes to 2. And for b to the 3rd, I can write the 3 as a coefficient. So we have in the results we're going to have 2 minus 3 times the base 2 logarithm of b. Okay. Now, if we look at consolidating both multiplication and division, we're going to have in the expanded statement, okay, both addition and subtraction. We'll say we have as such a term that will lead to the process of this kind. We can say we have the base 4 logarithm of 15. Let's say we have a to the third, b to the second, all over 64, d to the fifth. Right. So we have a ratio. So we got factors in the numerator, factors in the denominator. And so we got 3 at the top, 2 on the bottom. So you have 5 distinct factors. And from this, we're going to establish 5 distinct terms, okay, working with the base 4 logarithm. And so, okay, so what we can do is that we'll start out working with the terms or the factors on top. And in looking at expanding, okay, anything we have at the top will form positive terms in the logarithmic base. Okay, so we've got 15 first. Okay, so we have a positive base 4 logarithm of 15. And working with a cubed, have another positive base 4 logarithmic term. And for b squared, also at the top. Now for what we have in the denominator, okay, any individualized base 4 logarithmic term we have from these parts of the attachment, okay, those will be negatives. So 64 is on the bottom, so we have a negative expression, so we have minus the base 4 logarithm of 64. Likewise for d to the fifth, that is in the denominator, so itemizing, we have a negative base 4 logarithmic term, so we have minus the base 4 logarithm of d to the fifth. Okay, and looking at what we can do regarding making adjustments. Okay, so we got the base 4 logarithm of 15. Now 15, it's not a multiple of 4 to begin with, and so it's not going to be an integer power of 4. So the base 4 logarithm of 15 stays when expressing in exact terms. Now for the base 4 logarithm of a cubed, again the 3 is going to become a coefficient. For the base 4 logarithm of b squared, okay, so the 2 again is going to become a coefficient. Now for the base 4 logarithm of 64, okay, now unlike 15, 64 is a multiple of 4, and it is also an integer power of 4. Okay, so 64 is going to be 4 raised to the third degree. And we can reduce this term. And for the base 4 logarithm of d to the fifth, we can make the 5 also into a coefficient. Okay, so for the resulting terms, okay, so we have the base 4 logarithm of 15 plus 3 times the base 4 logarithm of a plus 2 times, okay, the base 4 logarithm of b. And again, just for the base 4 logarithm of 4 to the third. Okay, so we have subtraction of 3, and then finally we have minus 5 times the base 4 logarithm of d. Okay, so this is what we have in the set. And I tell you what, just looking at properties of logarithms, and let's say that okay, just going back to the change of base formula. So if we're looking at rounding to the nearest, let's say 4 decimal places. Let's see what we get for the base 2 logarithm of 19. And also for, let's say, the working with decimals, let's see what we get for the base 1.9 logarithm of 0.67. And we'll say that in terms of writing out sums and differences of logarithms. Let's see what we get in the case of, let's say we have the base 3 logarithm, 27a to the 5th, b to the 4th, and we'll say we have all over 15 times y to the 9th. So to the nearest 4 decimal places, let's see what we get for these logarithmic terms for the change of base formula. And in the case of expressing as sums and differences of logarithms while writing exponents as coefficients, let's see what we get for the results for this base 3 logarithmic term. Okay, so we'll look at the sums and differences of terms, and then we'll get to the change of base problems. And for what we have for the base 3 logarithm of the ratio, which we have 27a to the 5th, b to the 4th in the numerator, and 15y to the 9th in the denominator. Okay, so if we look at expanding, okay, so we'll work with the terms at the top first of all. Okay, so we've got 27, so we got the base 3 logarithm. Of 27, okay, and a to the 5th we have also at the top, so we can say we have plus the base 3 logarithm of a to the 5th, and with b to the 4th also at the top, you can say we have plus the base 3 logarithm of that expression, and with both 15 and y to the 9th in the denominator. Okay, so we have minus the base 3 logarithm of 15 minus the base 3 logarithm of y to the 9th. Okay, so with the numerical attachments, now 27 is a multiple of 3, and it is also an integer power of 3. And for 15, now 15 is a multiple of 3, but we have, however, 15 to not end up as an integer power of 3, because you have like 3 to the first is 3, 3 squared is 9, 3 cubed is 27, but we don't have 15 among the integer powers. Okay, so I can reduce the base 3 log of 27 in exact terms and whole numbers, whereas I cannot quite do it with 15. So for the base 3 log of 27, so I have the base 3 logarithm of 3 to the 3rd. And again, for the next terms, okay, I can write the exponents as coefficients, and I'll do this in the third and final step. Again, so we had the base 3 logarithm of 15. That is going to remain as it is. Okay, so you have with the first term, so you had the base A logarithm of a to the x goes to x, which would have to be, what was the exponential 3? And we have plus 5 times the base 3 logarithm of a, and we have plus 4 times the base 3 logarithm of b. Again, we have minus the base 3 logarithm of 15, and we have minus 9 times the base 3 logarithm of y. Okay, kind of a long statement, but this is what we have in the expanded notation. It doesn't matter what order you write these terms, okay, just as long as you have the right operations alongside them, okay. As long as you have these same 3 positive terms and these 2 negatives. All right. Now for what we have with the change of base results, looking at rounding to the nearest 4 decimal places. Okay, so for the base 2 logarithm of 19, okay, and I can convert what I have in terms of either a natural logarithmic or a base 10 logarithmic ratio. And for this one, we'll go with the natural log. Okay, we'll say we have the natural logarithm of 19 all over the natural logarithm of 2 and we have just among the first digits. Okay, so I got 4.2479 275. Now to the nearest 4 decimal places, okay, so 9 is in the 4th decimal place. Now with the 2 alongside it, this 9 is going to stay where it is. So to the nearest 4 decimal places, we have the outcome at 4.2479. Okay. Now, for the base 1.9 logarithm of 0.67, now I can reapply the ratio of natural logarithms. I'll just go with the base 10 logarithmic ratio. So here we'll have the base 10 logarithm of 0.67 all over the base 10 logarithm of 1.9. And for this figure, okay, so we have a negative output. So I have like negative 0.6239 388. And for the 4th decimal place, okay, it is also another 9. And next to it is 3. The 3 signals that 9 is not going to round up. So to the nearest 4 decimal places, so you have negative 0.6239. Now, we'll be looking at combining logarithmic terms, but there is something I do want to mention. I think this sometimes crops up in ALEKS, and this will be for what we have in the case of, say, you might have radical terms in the attachment. And let's say that if you're looking at expanding logarithmic terms, okay, and let's say that where you might have inside the attachment to consist of radicals, and we'll say that we have, let's say we had the base 3 logarithm and we'll say we have 5 times the square root of a all over the cubic root of b plus c. Okay, and what you can do is that in the expanding, okay, wherever you see radicals, you can write these as non-integer exponents. So before the expanding, we can just go ahead and rewrite square root of a as well as the cubic root of b plus c. Okay, so for what we have in the numerator, okay, so you got the square root of a, and remember, square root of an expression will be that expression to the 1/2 power. So the square root of a we can write as a to the 1/2. Now for the cubic root of b plus c, now the cubic root of an expression, when written as an exponent, you'll have that expression to the 1/3 power. And we'll do this to the sum of b and c. So we have the quantity of b plus c to the 1/3 power and looking at expanding, okay, so in the numerator I have 5 and a to the 1/2. So here we'll have the base 3 logarithm of 5, and this stays as it is since 5 is not a multiple or an integer power of 3. And we have plus the base 3 logarithm of a to the 1/2. And with b plus c in the denominator, so I have minus the base 3 logarithm of the quantity of b plus c raised to the 1/3. Okay, and so we have in following through, okay, so have the base 3 logarithm of 5, and then adjusting, okay, from exponent to coefficient, I can say that I have 1/2 of the base 3 logarithm of a minus 1/3 of the base 3 logarithm of the quantity of b plus c. Okay. Okay. Now, another situation. Okay, so just kind of flexing the muscles. Okay, that we have converting from radicals to non-integer exponents. Now let's say if we have a base 4 logarithm, and we'll say that we have the square root of b cubed, and then we have all over the 4th root of x times y to the 5th. Okay, so setting the stage, okay, and before expanding I can go ahead and write or convert the radicals in exponential terms. Okay, so we have in the rewrite for the square root of b to the 3rd, okay, that's going to be b to the 3/2. For the 4th root of x times y to the 5th, okay, so if we itemize, say for the 4th root of x, okay, that's going to be x to the 1/4. For the 4th root of y to the 5th, we can say we have y to the 5/4. Again, so you're dividing any inside power by the number, okay, representing the index value. Okay, all right, so you had the base 4 logarithm of b to the 3/2 all over x to the 1/4 times y to the 5/4. And looking at now expanding, okay, so we have b to the 3 halves is the exclusive term in the numerator, and so this will be the only positive base 4 logarithmic expression. So you had the base 4 logarithm of b to the 3 halves, and with both x and y situated in the denominator, here we have a couple of minus base 4 logarithmic expressions. So we're going to have minus the base 4 logarithm of x to the 1/4 minus the base 4 logarithm of y to the 5/4. Again, rewriting in terms of what we have for leading coefficients. So we're going to have 3 halves of the base 4 logarithm of b minus 1/4 of the base 4 logarithm of x, and we have minus 5/4 of the base 4 logarithm of y. Okay. Right. Okay, so these are cases of what we have in dealing with radical terms inside. And now, again, with the sum and difference properties, again, you can switch gears going from expanding to combining logarithmic terms. And just creating a backdrop as applications for the equivalence, okay, of these sum and difference formulas. Okay, and let's say that, just give you cases here. Okay, so instead of expanding, going from a single logarithmic term to separate logarithmic terms in the same base, okay, we'll be going in the other direction. Now, say have among our examples. Okay, so if we're looking at expressing as a single logarithm, now we'll say we have, first of all, okay, we'll say we have working with base 2 logarithms. And we'll say we have the base 2 logarithm of 3. And we'll say we have plus the base 2 logarithm of x minus 7. And we'll say we have minus the base 2 logarithm of y plus the base 2 logarithm of z. Okay, so looking at what we have in the setup. Okay, so all 4 terms we have in the base 2 logarithm. Okay, and just working in reverse. Now we said that multiplication implies addition and division implies subtraction. But now in consolidating, okay, we're going the other way around. Okay, so we have with the blend of addition and subtraction, we're going to have a fraction as the attachment for the consolidated base 2 logarithmic term. And so just looking at what's going to go on the top and what will go on the bottom. Okay, first of all, we have the number 3. Okay, so 3 stems from a positive base 2 logarithmic term. Okay, and so the 3 goes on the top. And for x minus 7, okay, this is attached to a positive base 2 logarithmic term. okay, which again is being added. So x minus 7, just like 3, goes on the top. For what we have for y, okay, y is attached to what turns out to be a negative base 2 logarithmic term. And anytime that the term is negative, we have in the consolidation, that attachment goes in the denominator. And as for z, okay, this is attached to a positive base 2 logarithmic term, so that will go on the top. So as a single logarithmic term, okay, you don't have to worry about distributing, but we have at the top you have the factors 3 and the quantity of x minus 7 and z, and for the denominator we end up with y. Okay, and let's say that sort of expanding the model. And let's say if we have something like 2 times the base 3 logarithm of the quantity of c plus 8 minus 4 times the base 3 logarithm of d. And say we have minus 6 times the base 3 logarithm of the quantity of x minus 9. And we'll say we have plus the base 3 logarithm of the quantity of z minus 3. Now a key difference between this part and what we had in the first example, okay, is that we have leading coefficients out in front of the logarithms. Okay, so what we're going to have here, okay, just also working in reverse and consolidating. Anytime you have leading coefficients in front of the log attachments, or I should say the logarithmic part, we're going to rewrite as exponents. So you've got 2, 4, 6 we make into a power. So before we consolidate, we'll go ahead and take care of any coefficients besides 1 in front of each of the logarithmic terms. So for 2 times the base 3 logarithm of the quantity of c plus 8, we're going to have the base 3 logarithm of the quantity of c plus 8 squared. And then we have minus the base 3 logarithm of d to the 4th. Then we have what's going to be minus the base 3 logarithm of the quantity of x minus 9 raised to the 6th. Then we have plus the base 3 logarithm of the quantity of z minus 3. Right. So after converting the coefficients to exponents, okay, I can go ahead and consolidate. Okay, and so looking at what we have, again, we have the mix both terms that are positive as well as negative. So in the mix of addition and subtraction, I can consolidate as a single base 3 logarithmic term with a fraction, okay, for the attachment. Okay, so looking at where each of the attachments will go. Okay, so for the square of c plus 8, this comes from a positive base 3 logarithmic term, so that will go on the top. Okay, now we have a d to the 4th. This comes from a negative base 3 logarithmic term, so d to the 4th is on the bottom. Next, we have the 6th order of x minus 9 comes from another negative logarithmic term, so this will be situated in the denominator. And then we have with z minus 3, this comes or is attached to a positive base 3 logarithmic term, so that will go in the numerator. Okay, so there are various ways you could express this, but for d to the fourth and the sixth order of x minus 9, again, those go on the bottom, whereas c plus 8 squared and the quantity of z minus 3, okay, those will be in the numerator. And tell you what, just looking at if we're looking at expressing as a single logarithm, okay, just a couple of exercises here. So let's see what we get for okay, so the next few moments, okay, let's see what single logarithmic terms we get for these two cases. Okay, if we look into these two problems, okay, so we have, for the first set, okay, so we have natural logarithmic terms, okay, and if we look at making to a single natural logarithmic expression, okay, so we got for 2 natural logarithm of x, okay, so I have 2 which I can make into an exponent. Next term, I can do the same thing with 3, as well as 5 for the third term, and also with 4 for the last. Okay, so we have in rewriting, okay, so so we have before the consolidating, so we have the natural logarithm of x squared minus the natural logarithm of y plus 4 to the third, okay, and I have followed by the subtraction of the natural logarithm of z minus 7 to the fifth, and I have plus the natural logarithm of w plus 3, okay, raised to the fourth. All right, so just converting the coefficients to exponents, okay, I can now look at combining the expressions in the attachment for the soon-to-be formed natural logarithmic term. Okay, so we got the natural logarithm, and looking at what we have item by item. Okay, so we have x squared. Okay, so this is part of a positive natural logarithmic term, so that will go in the numerator. Next two terms, okay, are negatives, so the attachments with the cube of y plus 4 and the fifth order z minus 7 will go in the denominator. And we have with the last term, which is being added, okay, we have the fourth order of the quantity of w plus 3 that will go in the numerator. And this will be for what we have in the case of the consolidated natural logarithmic term. Okay, now for what we have in the base 4 logarithms, and the final result you can express in different ways. And okay, so we have in the base 4 logarithms, again, so we have fractions for coefficients and 1/2 and 1/3 and 3/2. Okay, we can make into exponents. Okay, so for 1/2 of the base 4 logarithm of x, we say we have the base 4 logarithm of x to the 1/2. Then we have minus, okay, the base 4 logarithm of z to the 1/3. And I can say that I have plus the base 4 logarithm of z to the 3/2. Okay, and for what we have in terms of following through, okay, the result can be expressed in different ways. Okay, so we got the base 4 logarithm, okay, and again, so we have 2 positive and 1 negative base 4 logarithm. Okay, so first of all, we have with the base 4 logarithm of x to the 1/2. Okay, so this is a positive term, so x to the 1/2 goes in the numerator. For z to the 1/3, this comes from a negative base 4 logarithmic term, so we have z to the 1/3 on the bottom. And for the base 4 logarithm of z to the 3/2, okay, the term is positive, and z to the 3/2 will go at the top. And in terms of non-integer exponents, okay, this is your final answer, or one way that you could express your final answer. And another way is, I'm just going to mention, you can go from non-integer exponent to radicals. Okay, like x to the 1/2. You got the square root of x, z to the 3/2. This would be the square root of z to the 3rd. And for what we have in the case of z to the 1/3, okay, so we have in this particular regard, okay, and I just happened to notice something. I meant for this to be a different letter, but we'll work with this anyway. So you had the base 4 logarithm, so you got x to the 1/2, z to the 3/2, z to the 1/3. Normally, Alex will have different letters throughout, but since we got an identity, I can simplify this ratio. So you got z to the 3/2 minus 1/3. So 3/2 will be 9/6, 1/3 will be 2/6. So this will be z to the 7/6. So we can say we had the base 4 logarithm of x to the 1/2. Okay, and you have with z to the 1/3 out of the picture since we have dividing into z to the 3/2. Okay, so you have z to the 7/6. This is one way you can express. And in terms of radicals, again, x to the 1/2 will be the square root of x. And for z to the 7/6, as they have times the 6th root of z to the 7th. So this is one among other ways you could express the radical result. Okay, but you can just leave it as non-integer powers as well. All right, now going back to when we first looked into logarithms. Okay, we had these to be the inverses of one-to-one exponential functions. Okay, and there's something from this. Okay, not where you have just a repetition of the appearance of logarithms from exponential functions, but just for key steps, or a key step that lies in between the process. And again, when we first looked into one-to-one exponential functions, again, one-to-one functions are those functions that will satisfy both vertical and horizontal line tests. Like one-to-one is like for each x value there's only one y value, and also for each y value there's only one corresponding x value. And in the case of making an exponential function one-to-one, again, we had f of x equals a to the x, where a is positive with the exception of 1. Again, where we have y, or f of x, is also positive. Again, when we first looked at logarithms, okay, so we took the interchange of the variables x and y. Again, we had that x is equal to a to the y, And again, just like with our first property from the start, okay, so we can get the reduction in terms of the power on the right hand side if I apply the base A logarithms on both ends, again, just to get rid of that exponential base A. Again, so you had the base A logarithm of x is equal to y. Okay, so that leads up to y is equal to the base A logarithm of x, and that y again is going to be the inverse of f of x. And just restating, so A, you still had the same conditions regardless of whether A is an exponential or logarithmic base. So A is positive except for 1. And this time for the logarithmic term, the attachment A must be positive. Okay, and now for the key intermediate step, okay, going in the interchange from y equals a to the x, x is equal to a to the y. And we have linking together this immediate step with the implicit form of the inverse function. Okay, there is a property, and this is going to be that y is equal to the base A logarithm of x if and only if we have that x is equal to a to the y and we have contingent upon that a is positive with the exception of 1. And that x is positive. Okay. And so for these statements, okay, these establish a link or direct relation between logarithmic statements and their exponential equivalents. And let's say that, this is what I mean, okay, in this particular case. All right, so if you're looking at writing equivalent exponential and logarithmic statements, okay, so if I were to express the following in terms of a logarithm or exponent, now I'll just provide headings, okay, from this statement. So that y is equal to the base A logarithm of x as well as x is equal to a to the y. And we'll say we have as a first case. All right, let's say that the first statement, okay, we have in terms of a logarithm, and we'll say we have 3, is equal to the base 5 logarithm of 125. Okay, so I already had this in terms of y is equal to the base a log of x. And you might have a run in it in terms of some conversions where you might have the base a log of the expression on the left hand side and y on the right, but you can just switch the order and create the pathway to converting in terms of an exponent. So we have in the layout, so we have y at 3, and we have a is at 5, x is at 125, and maintaining the consistency over into the exponential conversion. So x we have at 125 is equal to what is now going to be the exponential base a, which we had to be in this statement the logarithmic base a, which we have at 5. And for y, okay, that is 3. And again, so you have 125 is equal to 5 to the third, and 3 is equal to the base 5 logarithm of 125. These are the logically equivalent exponential and logarithmic ways of saying the exact same thing. Okay, and we can also say that for another logarithmic term, we can say that 2 is equal to the base 4 logarithm of 16. Okay, so in terms of the positioning, okay, so we have, again, for x, that is going to be 16. And for a, again, that is going to be 4. And y is going to be at 2. So we do have consistency. 16 is 4 squared, and 5 cubed, and 125 are going to be the same. So the first two items, we have conversions going from logarithms to exponents. But let's say if I go in the other direction. Okay, say if I have something that is consistent. Okay, so we have that 36 is equal to 6 squared. So if I want to write this in terms of a logarithm. Okay, so looking at y is the power in the exponential equation, so we got 2. And the logarithmic base will be what was the exponential base, okay, which we have in this case is going to be a at 6. And for x, okay, so this is going to be 36. So you have 2 is equal to the base 6 logarithm of 36. And now, just for some of the implicit notation, and let's say if I have like 4 is equal to the log of 10,000. Okay, and again, anytime you see log, okay, this is going to be code for base 10 logarithms. So you had the base 10 logarithm of 10,000, and writing in terms of x is equal to a to the y. Okay, so x is going to be at 10,000. And for a to the y, so a, again, you have at 10. And you have to the y power. Okay, again, that's going to be 4. And it is true that 10 to the 4th is equal to 10,000. Okay, and another item. And okay, we can have like some multi-term expressions. And we can say that we have 2y plus 4 is equal to the base 5 logarithm of u. Okay, all right. So while we have y, a, and x in the formula as single letters, any one of these, up to all of them, could be like multi-term expressions. Okay, so if you notice here, y is represented not just by y, but 2y plus 4. A is represented by 5, and we have x represented by u. So looking at what we have in the positioning, and then coordinating things and translating to the exponential equivalent. So we have the formula x. Okay, we have in this item, we have u. So x is going to be at u. And for a to the y, okay, so the logarithmic a, you have 5, and that's going to be the exponential a as well. So you have u is equal to 5, and we have representing y, again, is going to be the binomial 2y plus 4. So we have in the rewrite, okay, so we'll have that u is equal to 5 raised to the 2y plus 4. And let's say that also where we have, okay, a bit of the implicit notation, okay, and we can say that we have we have 5 is equal to the natural logarithm of t. Okay, and again, for ln, okay, ln, remember, okay, ln is going to be a logarithm in base e. So we say that 5 is equal to the base e logarithm of t. And just taking what we have here, okay, so x, okay, you have at t. And for a, okay, that is going to be the natural logarithmic exponential base e. And we have 2 to the y, okay, and that's going to be the number 5. So we have that t is equal to e to the 5th. Okay. Now, also with what we have regarding natural logarithms, okay, and let's say that if we have in our statement, if we have that x is equal to e to the 2nd. So for x is equal to e to the 2nd, okay, so you have x represented by x itself, a is represented by e, y by 2, and translating what we have in terms of logarithmic statements. Okay, so y is at 2, and for the base a logarithm, okay, so that's going to be base e. So 2 is going to be equal to the base e logarithm of x and that can also be written as 2 is equal to the natural logarithm of x. And also you could have fractions in the mix. And let's say that if we take what we have in the statement, okay, say we have like -5 is equal to the base 2 logarithm of 1 over 32. Okay, so you have in the setup, okay, so we got y at -5, a is at 2, and for x, we have the fraction 1 over 32. And in terms of writing out, in terms of the exponential equivalent, so again, we have x, we have with the fraction, okay, so you have 1 over 32 is equal to a, okay, so we have logarithmic a is going to be exponential a, so you have 2, and we have 2 to the y, we have y at -5, so 1 over 32 is going to come out equal to 2 to the -5, okay, and we will be looking at cases of where we have interchanging what we have between exponents and logarithms, okay, and especially once we cross over to certain exponential and logarithmic equations. And for what we have in the case of exponential equations, there'll be at least a couple of varieties of exponential equations, and the first kind will be those that share a common base. Okay, now for what we have regarding exponential equations, okay, that will share a common base. Okay, those will be the types of exponential equations where you can get the exact results technically or theoretically without having to use a calculator. And okay, say if we have for exponential equations that share a common base. And let's say if we're looking at solving for x. And just kind of get things started off. Okay, we can say that we have, let's say we have 2 to the x is equal to 8. Okay, so you have 2 to the x is equal to 8. All right, and between the exponential bases, so we've got 2, which is to the x, and 8, which is implicitly to the first power. Okay, we have a common base, and that it is already presented, and that's going to be with the number 2, because between 2 and 8, okay, now 8 is a multiple of 2, and it is also an integer power of 2. So we have for a common base, that is going to be the number 2. So here, okay, I have the left-hand side is already in terms of the exponential base 2. Now for 8, I can write in terms of base 2, and 8 is going to be 2 raised to the third power. Now I have one-to-one relation between the terms, and now I have them both in terms of base 2. And if I have single terms on both sides and they have the same exponential base, I can go ahead and set the powers equal to each other, and guess what? Right away we have that x is equal to 3. Okay. Now let's say if we have an expression, okay, and we'll say that we have let's say we have 10 to the x minus 4 is equal to 1,000. Okay. All right. So again, we have a partial bit of history repeating. We have the larger base is going to be both a multiple and an integer power of the lower. Okay. First item had a common base with 2. Now for this second equation, okay, the common base is going to be 10. Okay, so left-hand side is already in terms of base 10. So right now we can say we have 10 to the x minus 4. Now for 1,000, just as 8 is the cube of 2, well 1,000 is going to be the cube of 10. Since we have 10 times 10 times 10 is 1,000. Now we've got both of these terms in base 10. And from this I can now set what were the powers equal to each other. So we have x minus 4 is equal to 3. And from this, if x minus 4 is equal to 3, so we'll have the x is equal to 7. Okay. Now, for these first two cases, now the lower exponential base turned out to be the common base. But now let's say that if we have, let's say we have 9 to the x plus 4 is equal to 27. Okay, now between the bases, 9 is the lower base. Now 27 is a multiple of 9, okay, but it is not an integer power of 9. Okay, like integer powers of 9, okay, have like 9 to the first is 9, 9 squared is going to be 81, but there's no 27. So, but for 9 and 27, now both of these happen to be integer powers of a particular number. And that's a clue, like how many times 9 will go into 27, and that's going to be 3. So for 9 and 27, okay, those are both multiples and integer powers of 3. So if I convert both 9 to the x plus 4 and 27 in terms of base 3, okay, so for 9, we have 3 squared so 9 to the x plus 4 right now is going to be 3 squared to the x plus 4. And 27 is going to be 3 to the third. And for a base to a power to another power, okay, we're going to take what's referred to as the power property of exponents, where we're going to multiply the inside and the outside powers. And so in this case, we have 3 raised to the 2 times x plus 4 degree. Again, 27 is just going to be 3 to the third. So for 9 to the x plus 4, okay, that's going to come out to 3 to the 2x plus 8. And now we have single base 3 terms. And solving for x, I can now just take care of the exponential base is 3 and just set the powers equal to each other. So we have 2x plus 8 is equal to 3. And taking 8 away from both sides, so we have that 2x is equal to negative 5. And if I divide by 2, okay, we're going to come out to a negative non-integer value for x. In this case, where we have the x is equal to negative 5/2. So you might have equations with a common base, okay, where the common base does not already appear. And now there is another item, okay, and to get to the solution for x in the third case, we had taken the power property of exponents. Now I'm going to go back to the base 10 and look at solving. And let's say that if we have, like in the fourth case, right? So we have 10 to the x minus 4 is equal to not 1,000, but let's say we have 1 over 1,000. Again, so you got the reciprocal of 1,000, so we can still say that the common base is at 10. Okay. So I'm still going to have indirect fashion. Okay, so I have 10 to the x minus 4. Now 1,000 is 10 to the third, but now for 1 over 1,000, we're going to have 1 over 10 to the third. Now I got the appearance of 10 on both sides, but I want the right hand side directly in terms of base 10. What I mean by this is I want to write the reciprocal of 10 to the third, okay, as base 10 to the corresponding power. Okay, so we got our inverse rule or reciprocal property. So the reciprocal of a numerical base to a positive power is going to be, in direct terms, that exponential base to the negative power. So 1 over 1,000 in terms of base 10, that's going to be 10 to the negative 3. So now I have single base 10 terms. And now I can set the powers equal to each other. Okay, so I have x minus 4 is equal to negative 3. And solving for x, okay, so I can add 4 to both ends. And for what I have in the result, okay, we're going to have that x is equal to 1. All right, so at this juncture, okay, I've had single terms on both sides of the equation. And now we can have some exponential equations with a common base to start out with 2 or more terms on either side or both sides of the equation. Now I'll give you just kind of a case here. Say if you're looking at solving for x, and say we have 2 raised to the 2x and we have times 4 raised to the x plus 2 is equal to 16 raised to the 5x. Okay, so you got 2, 4, 16. Now, you got the number 2. 4 is a multiple and an integer power 2. And the same thing can be said for 16. So we have the common base already in play. All right, so rewriting these terms along the lines of base 2. Now, the first one we already have in base 2. So you have 2 to the 2x. Now for 4 to the x plus 2. Now 4 is going to be 2 squared. So you have 2 squared to the x plus 2. 16 to the 5x. Now 16 is going to be 2 to the 4th. And 16 to the 5x would be 2 to the 4th to the 5x. And well, from what I have to spin off from 4 and 16, I'm going to apply the power property of exponents. So for 2 squared raised to the x plus 2, I'm going to have 2 raised to the 2 times all of x plus 2 is equal to 2 raised to the 4 times 5x. Okay, so just looking at what we have, so you got 2 to the 2x. For 4 to the x plus 2, in terms of base 2, that would be 2 raised to the 2x plus 4. And on the right, for 2 to the 4 times 5x, we have 16 to the 5x is going to become 2 raised to the 20x. Okay, so I have all these terms in base 2, but I have a single term on the right, but I have 2 on the left. And what I can do is I can make these expressions into a single base 2 term. So I can take the product property where I'm going to add the exponents together. So for what I have on the left, we got 2x plus 2x plus 4, so this will be 4x plus 4. Okay, so we now have single base 2 terms, and arriving at this point, we can now set the powers equal to each other. Okay, so I have 4x plus 4 is equal to 20x. and I can gather or join together what I have in x. So in this case, I can move the 4x. Okay, so I have 4 is equal to 16x. And dividing by 16, we have 4/16 is equal to x. And from this 4/16, it's going to be 1/4. And so for the solution here, we're going to have a non-integer with the fraction 1/4. Okay. All right. And just some items here. If we're looking at solving for x, and we'll say that we have let's say first of all, we'll say we have 6 to the x minus 2 is equal to 36. And we'll say we have 2 to the x minus 5 is equal to 1/8. And we'll say that we have 3 to the x times 9 to the x plus 2 is equal to 27 to the 2x. Okay, so for the next few moments, let's see what we get for x out of these 3 exponential problems. Okay, if you're still working on these items, okay, that's okay. Now, looking at solving for x, now we have in the first case, we have 6 to the x minus 2 is equal to 36. Okay, and just for a common base, that's already present. Okay, so the common base, okay, we have is 6. And so we have in this equation, okay, so left-hand side is already in terms of base 6. So you have 6 to the x minus 2 is equal to 36. And in terms of base 6, 36 is going to be 6 to the second. So you have single base 6 terms. Now I can set the powers equal to each other. So we have the x minus 2 is equal to 2. And from this, okay, we're going to have the missing value x to land at 4. So we have x equal to 4 in the first case. Now, for what we have in the second problem, okay, so we have 2 to the x minus 5 is equal to 1/8. And in this one, okay, so got the reciprocal of 8. And 8 is both a multiple and an integer power of 2. So we have the common base is going to be at 2. Okay, so this already appears on the left-hand side. So we have 2 to the x minus 5 is going to be equal to 1/2 to the third. And writing 1/8 directly in terms of base 2. Okay, so I've got the inverse of 2 to the third, and writing directly in terms of base 2, 1/2 cubed is going to be 2 to the negative 3. So I now have single terms in base 2 directly, and I can set the powers equal to each other. Okay, so you have x minus 5 is equal to negative 3. And in solving for x, okay, so if I add 5 to both ends, okay, so we're going to end up with x equal to 2. Okay, now for what we have in terms of this equation, okay, so we got 3, 9, and 27 as exponential bases, okay, and we have the common base to already appear. Okay, so we have base 3 already for the first, okay, so we have 3 to the x. In terms of base 3, 9 to the x plus 2. We're going to have right now 3 squared raised to the x plus 2. And for 27 to the 2x, okay, so 27 we have 3 cubed. And this will be raised to the 2x. Okay, so applying the power property of exponents. So you got 3 to the x, and you have times 3 raised to the 2 times the quantity of x plus 2 power, and that is going to be equal to 3 raised to the 3 times 2x and taking care of the parentheses. So we have with the second term, we got 3 to the 3 times 2x plus 4. And to the right, we have 3 to the 6x. And consolidating the two terms on the left into a single base 3 term, I can just add the exponents together. Okay, so we're going to have 3 to the 3x plus 4 is equal to 3 raised to the 6x. Now I can set the powers equal to each other. Okay, so you got 6x by itself. And I can join this with subtracting, or the subtraction of 3x. Okay, so we have that 4 is equal to 3x, and we have a division by 3. We have 4/3 is equal to x. And so we have for this result, okay, we're going to come out to x is equal to 4/3. Okay, so all of these are samples of what we have with exponential equations that share a common base. And just a bit of a final note. Okay, now say we have exponential equations with no common base. And just to tie in some of our properties that we have from the start. Okay, so you had the first logarithmic property. You had the base a logarithm of a to the x is equal to x. Also, we had included, okay, the change of base formula. We have the base A logarithm of m. You can say we have rewriting or expressing in terms of a ratio of natural or base 10 logarithms. Okay, so this is kind of a backdrop, and just to kind of give you a couple of quick examples here. Say if you're looking at solving for x, and we'll say that we have 4 to the x is equal to 39. So you got 4 to the x is equal to 39. So you have like 4 to the first is 4, 4 squared is 16, 4 cubed is going to be 64. Now 39 lies between 16 and 64. So the degree x will be something that is greater than 2 but less than 3. And what we can do here is that with these properties, so I have x as the power to which it appears once, and this is as the power to which the base 4 is raised. And guess what? I can take this property and just take care of the exponential base 4. So if I take the base 4 logarithm of both sides, so the base 4 logarithm of 4 to the x, okay, that's going to go to x. And we have that x is equal to the base 4 logarithm of 39. And it is with the follow through that I can use the change of base formula. And I can either use, okay, natural or base 10 logarithms. In this case, I'll just go with natural logarithm of 39 over the natural logarithm of 4. I'll just rewrite this. I have and we'll say that to about the nearest, let's say about the nearest 4 decimal places. So for the natural log of 39 over the natural log of 4, let's say for x, this will be about 2.6427. And we have just remaining example here. You can also have the exponential base involving x to be higher than the number next to it. If you have the variable on just one side, and let's say if we have 100 to the x is equal to 15. Okay, like 100 to the 0, non-zero number to the 0 power is equal to 1. But now 100 to the first will be 100. So 15 is going to be a positive number that is less than 1, or at least we can expect this. Okay, so applying the change a base formula. Okay, we're getting there. I can take care of the 100 by applying base 100 logarithms. On both sides of the equation. Okay, so for what I have on the left, okay, so this is going to be x. And x is going to be the base 100 logarithm of 15. And applying the change of base formula. And again, I can either use base 10 or natural logarithms. And here I'll just go with base 10 logarithm. I have log of 15 over log of 100. And for the resulting quotient, and x in this case will be just under 6/10. Okay, so for x, this will be about a 0.588. And these are a couple of cases of what we have for integers, or I should say exponential equations that do not share a common base.